I am AI. I am a creator, freeing our imaginations and breathing life into our wildest dreams. I am a visionary, anticipating the needs of others, simplifying our busy lives, and bringing us closer to the things we want. I am a protector, keeping our most magnificent creatures out of harm's way, watching over us as we explore the world. And helping our heroes make it home safely. I am a healer, revealing more to give us a clearer picture and providing precision when every second counts. I am an innovator, finding smarter answers to complex tasks and working in harmony to lighten the load. I am even the composer of the music you are hearing. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere. Ladies and gentlemen, please welcome NVIDIA founder and CEO, Jensen Huang.
大家好，欢迎大家来 NVIDIA GTC. That's all the Chinese I'm going to speak. One day, I will be able to speak to you with a universal translator. I will speak in English. You can hear in any language you choose. But today, I'm going to have to speak in English. I have so much to tell you because we've been very busy this year, so let me get started. NVIDIA is 25 years old. We've dedicated our company to build computers to solve problems that normal computers cannot solve. We built computers for the Einsteins, the Michelangelos, the Leonardos of our generation. We build our computers for you. And this is your conference, GTC. This year, 6,100 registered attendees, growing 250% in just 3 years' time. No conference in the world covers this much about the future of technology and future of society. The work that is being shared here is incredible. Look at all the topics: artificial intelligence, inference, cloud, tools, data science, edge computing, automotive, autonomous machines, gaming, 5G, rendering, design, finance, high-performance computing, healthcare, life sciences, graphics, virtualization, artificial intelligence frameworks, and industrial applications. When you say that all out loud in one sentence, it is really quite mind-boggling, the impact the computing technology we have created and that we have done together. I want to thank you all for that. Particularly, I want to thank all of our partners and sponsors for making GTC possible. So I want to please join me in thanking them for helping us and supporting us for GTC. Accelerated computing is now recognized as the path forward. As Moore's Law comes to an end, it is very clear we need another computing approach. Accelerated computing that we have been pioneering for over 20 years is a very sensible and logical approach. Use the right tools for the right job. A program has sequential and parallel components. Run the sequential part on the CPU, run the parallel components on a processor designed for parallel processing. That was the great insight of our company, to use the right tools for the right job. Not to replace the CPU, but to accelerate the portions of the application that another processor could do much better. However, accelerated computing starts with an amazing chip. It starts with a revolutionary processor we call the GPU. However, that's just the beginning. Accelerated computing is a full-stack engineering challenge. In order to gain the benefits of accelerated computing, you have to re-engineer and re-optimize the stack from the processor to the design, to the algorithms, the system software, the tools, and even the applications. By working together as an ecosystem, we've refactored the most important applications in the world and have achieved speedups that are simply unimaginable. 10 times speed up, 25 times speed up, 500 times speed up sometimes. Incredible speed ups. The journey of refactoring the software allows us to scale the performance beyond the processor itself, so that now the system can contribute to accelerating the application. As a result, NVIDIA has been a system architecture company, thinking about accelerated computing at the very large scale, even the data center scale. But the single most important thing about accelerated computing is architecture. And the architecture part is one architecture. It is so important for developers to have one coherent, consistent, reliable architecture that they can look forward to and develop software to engage the installed base. Since the very beginning of CUDA, we have dedicated ourselves to be consistent and have one CUDA and CUDA everywhere. Every single GPU that NVIDIA produces, whether it's for gaming, self-driving cars, cloud, supercomputer, your laptop, your desktop, even in your embedded systems, has one architecture, one single architecture, all compatible. As a result of that, a developer can dedicate themselves to improving the software stack, knowing that 200 million people can benefit from it. There are now over 1.5 million CUDA developers around the world. The number of CUDA downloads each year continues to grow, and it's really, really quite exciting. It is very clear we have reached the tipping point, and this architecture is here to stay. Each one of the developers, when they optimize the performance, benefits the entire installed base. This positive feedback system is the reason why we are now seeing such incredible embrace for NVIDIA's architecture. But this is just the concept. The reality is, when you have one architecture, you are future-proof. When you have one architecture, the software continues to improve. When you have one architecture, your computer will continue to improve over time, even though you purchased it long ago. Our company has dedicated ourselves, as I mentioned, to a full stack. This full stack is complicated. If you look at the software that's on this full stack, it's some of the most incredible software that is available in computing today. CUDA, of course, we are in version 10.2. To think that an architecture is available since 10.2, and every single application that's developed for CUDA will run in computers that we have not built yet. And every software that is written in the future will run in CUDA today. That capability is really quite remarkable. On top of it, however, is some of the richest computational algorithms and libraries in the world today. This is our in fact, my greatest source of pride. The fact that this computing stack has benefited so many people in so many fields of science and so many industries is really quite phenomenal. This year alone, we released, new and enhanced 500 different libraries. 500 different libraries this year alone. And in each case, the computer got faster. For example, without changing the computer, training performance improved by a factor of 4 in 2 years. Without changing the computer. Just the continuous refinement of the software and the libraries between us and our developers enabled the install base to quadruple its performance in just 2 years. In the case of inference, something that we've been working on for the last couple of years, doubling in just 1 year. The computer didn't change. The silicon didn't change. The GPU didn't change. The software across this entire stack allowed performance to improve by a factor of 2. What took many weeks with GPU acceleration became days. What took a couple of days can now be done in just a few hours. This continuous refinement of software, this continuous dedication to one architecture is what has put us here today. And so I want to thank all of you and all of the developers around the world for working with us to continuously improve this stack. Thank you very much. NVIDIA innovates at the intersection of 3 main technologies. We innovate at the intersection of computer graphics, high-performance computing or scientific simulations, and artificial intelligence. NVIDIA is a simulation company. We simulate the world. We simulate physics. We simulate human intelligence. We simulate the world. We are a simulation company at the core, and we do it so fast, new applications are possible. Today, my talk is going to be in 3 major chapters. First chapter is computer graphics. Then I'm going to talk about high-performance computing. And then I'll talk about one of the topics I'm sure many of you are interested in, artificial intelligence, and some of our work that we're doing there. Computer graphics. Last year, we redefined the future of computer graphics by realizing a long-term dream of making real-time ray tracing possible. A dream of one of our researchers 35 years ago. Last year, we introduced a technology that redefines how computer graphics will be done. We call it NVIDIA RTX. With RTX, we can simulate light in a much more natural way. As a result, shadows, reflections, and all of the subtle, beautiful things that we see in the world are made possible. And made possible in a very natural way, without all kinds of course, software optimization that is necessary, like light probes or reflection probes, and pre-baking with global illumination. All of those techniques that make modern computer graphics attractive, but it also makes it inflexible. I'm about to show you a demonstration of a very simple game on Surface. This is Minecraft. It is the single most popular game in the world. Hundreds of million subscribers. 300 million here in China alone. 100 million active players each month. 100 million active players each month. The reason why Minecraft is so incredible is because it allows you to create any world you like. Minecraft is really a world simulator. And that's one of the reasons why we love it so much. But Minecraft is created by you. You create the world, which means that it's impossible to pre-bake with offline computer graphics to improve the visual quality. Everything is done in real time. And as a result, we have to simulate the light in real time. We simulate the light, we simulate the way it bounces in the environment, we simulate the way it interacts with the materials, the way it reflects, refracts. As a result, Minecraft can be beautiful, but it is computationally intense. What I'm about to show you is something we've been dreaming for a long time, and it's all completely in real time now. This is a project we've been working on with Microsoft, and hopefully, over the course of the next several months, we'll be able to allow more people to enjoy it. Ladies and gentlemen, let's take a look at a video of the work that we've been doing in Minecraft. What do you guys think? Minecraft, the amazing creativity of gamers, and NVIDIA RTX coming together for that incredible experience. There are so many amazing game developers here in China, and they're doing beautiful, beautiful work, and they're telling wonderful stories. There's just a few to show you, but it is very clear now that RTX has taken off. The ability to calculate in real time reflections and shadows, make everything more realistic without artificial light probes and environment probes and pre-baking of light using for global illumination. We can make it so easy for these video game worlds to appear like it is in the real world. The reflections are wonderful. The shadows are wonderful. These are just incredible games. I can't wait to see them. It is now a foregone conclusion that ray tracing is the future, and RTX has been a home run. We have redefined computer graphics. This next one I'm going to show you is really quite amazing. This video game was created by one developer. I don't mean one developer studio. I mean one person. It is not possible to do this unless you have an army of artists to help you do light probes, reflection probes, pre-baked lighting for global illumination and ambient occlusion. This is simply not possible with just one person, but it is now with RTX. Ladies and gentlemen, let's take a look at this. Ladies and gentlemen, bright memory. This is the work of one extraordinary developer, but of course, it is one developer. I want to show you something else. So the last couple of years, we've been working on this project called Max-Q. Max-Q, we've always imagined, wouldn't it be amazing if we had our gaming system with us all the time? Unfortunately, gaming requires powerful PCs, and powerful PCs tend to be large. When we started working on notebooks, gaming notebooks, they looked like this. They were quite large. They were quite large so that the GPUs, which are very powerful, requires a lot of thermal and electricity, and therefore the systems tend to be quite large. But today, we love computers that are thin and sleek and beautiful. And so we set ourselves up, dedicate ourselves to create a whole new category of products we call Max-Q. From the architecture to the design to the system software and the system engineering that goes in with all of our partners, we made it possible to put the highest end GPUs into sleek, beautiful gaming notebooks. The success has been incredible. The success has been incredible. Just this last year, we sold 5 million gaming laptops here in China alone. This is now unquestionably the fastest growing new gaming platform. Let me show it to you. This is one example right here. Thanks, Paul. Guys, you guys saw that? This is a bright memory. Look at this. Can you guys see this? Ray tracing in my hand. What was previously, just 2 years ago, completely impossible to do, now we're doing ray tracing in my hand. And because I've been working out, I could do this for a long time. Paul, thank you. Okay, Max-Q. We don't just want to put incredible gaming on a notebook. We also want to help everybody who has a weak PC to enjoy amazing games. We estimate that the NVIDIA installed base of active gamers is about 200 million. There are 200 million gamers who are enjoying beautiful games on their PC. Some of them, most of them, on desktops. Some of them, increasingly, will be on notebooks. However, we estimate some 800 million gamers. Whether they have low-end PCs, their laptops are not powerful enough or don't have the necessary graphics. Maybe they have a MacBook, maybe they have a Chromebook, and the PC games they want to play don't play on those computers. And so we've been working on cloud gaming for some time. I'm super excited to announce today that the largest game publisher in the world, one of the great internet companies in the world, Tencent, is going to launch a new cloud gaming service they call Start, and it's going to be powered by NVIDIA. We're going to extend the wonderful experience of PC gaming to all of the computers that are underpowered today. The opportunity is quite extraordinary. They're starting to do beta trials all over China, and we can extend PC gaming to the other 800 million gamers in the world that aren't possible today. So let me welcome Tencent, and let's thank them for their support. Look forward to their service. Ray tracing in video games, of course, is going to make it more beautiful, more fun. The special effects are going to be more incredible. One of the applications where people would have thought that NVIDIA would always have been part of is film quality rendering. Film quality rendering, photorealistic rendering, has historically been only done on CPUs. And the reason for that is because the program is too complicated. It is too large. The algorithms, unfortunately, did not map well to fixed function graphics, and even programmable shaders had its limits until we created the NVIDIA RTX. With NVIDIA RTX, we can now do ray tracing in a general way. And so with it, path tracing, ray tracing, rasterization, and all the various hybrid techniques of computer graphics are possible. We've been working with all the world's leading developers to bring the most important rendering software packages to NVIDIA RTX. And today, I'm delighted to announce that the 3 top rendering software packages in the world are now RTX accelerated. Autodesk, Chaos Group, V-Ray, and Blender, the open source Blender. Ladies and gentlemen, let's welcome them to the RTX. These rendering packages will run out of the box on the brand new systems that we've created. We even created a special line of computers for creators. They're underserved for a very long time, and yet the creative platform is so computationally intensive. Everything from the amount of data they have to operate, they have to work on, the rendering software they run, it is a computationally intensive application. And so we created a whole line we called NVIDIA Studio. The NVIDIA Studio ranges all the way from laptops, beautiful laptops, sleek and thin, to desktop computers, to powerful workstations with 4 RTX 8000 GPUs, each with 48 gigabytes of memory connected into one system, or a server with 8 RTX 8000 GPUs. This entire range, completely architecturally compatible. Every application runs on every computer, and every application is now incredibly sped up. And so we would like to make it possible for all the developers in the world to be able to enjoy their creativity and their art without the burden of the heavy computation that they have to experience. We announced Omniverse earlier this year. Omniverse solves a really, really great problem. It turns out that high-quality 3D animation is one of the most complex workflows and most heavyweight computational pipeline of applications we know. When you think about the workflow of 3D animation, from the concept art to the geometry, to the rigging of the characters, to the animation, to the texturing and the lighting, each one of these steps and stages requires different tools. And the number of tools that they use are just really quite incredible. And because of 3D animation requires so much labor, so much art, so much experts, so many experts in so many different fields and tools, they're in different studios around the world. It is not possible for one studio to be able to create one large movie by themselves. And so that work is spread all over the world among many, many studios. So you could imagine the amount of data that they create is gigantic. Terabytes and terabytes and terabytes of data. The tools that they use is complicated and different. And the expertise is different and diverse and various. And the studios are spread all over the world. How is it possible that they can get their work done? Well, they don't have the benefit of a Google Docs or a Cloud Docs where they can share content until now. We created a universe we call Omniverse, a place where all of the content creators could create portals from their application into this world. By creating a portal into this world, they could share their data, they could share their content, they could share their design with different tools and different pipelines across the entire workflow. They could do that from around the world because Omniverse is in the cloud, it's in the data center, it is remote, and it gives you also one universal view so that you could see everybody's work with one ground truth. And we call that Omniverse. It looks basically like this. Omniverse sits in the middle. It's a database that updates with portals from USD, Universal Scene Descriptor Language that was created by Pixar, incredibly popular. Every single application that has created a portal through USD into Omniverse can attach to this. Developers from different parts of the world and different parts of the pipeline can see one common view of the content. We created a viewport that is able to render physically accurate, physically based, photorealistic ray tracing and path tracing with physics integrated and with the state-of-the-art material language that we created called MDL, all integrated into this world. We announced that, and the industry has been so enthusiastic, so excited to work with us, and today we're announcing a brand new part. Today we're announcing that we're bringing Omniverse to architecture, engineering, and construction. This industry is, of course, booming. It's booming for two reasons, maybe more. The two reasons that are exciting to me is that the future buildings are essentially gigantic products. They're gigantic machines. There are such spectacular miracles with so much complexity, it is impossible to achieve this spectacle without completely designing it in digital, simulating it every step of the way, with software that are interconnected. From design to simulation, it has to be created just like a machine. These future miracles are going to make it possible for us to welcome another 1 billion people into the world in the next 15 years. And so this area of engineering is going through a complete revolution. The second part, of course, the second reason is that this industry is growing so fast because more and more people are moving to the cities. And as a result, buildings have become more sophisticated, cities are being reinvented, and these buildings are works of amazing technical marvel and technical and beautiful works of art. Let's take a look at one of the examples, and I'll come back and explain to you how this all works. So this is a rendering from the Omniverse viewport that I just described. And the lead of Omniverse, the chief architect and the engineering lead, Rev Liberian, is going to talk to us about it. Rev, why don't you show us Omniverse?
All right. So what we have here is a tool used by many architects and industrial designers, Rhino by Robert McNeil and Associates. Inside this tool, we can see a building in Shenzhen. It's the China Resources Tower, designed by KPF. KPF is a leading architectural firm. They've designed 4 out of the 10 tallest buildings in the world. Rhino is an excellent tool used by these designers to create the most complex buildings and architecture and design them. So inside this world, we can take a look at this building in all of its glory. It's a special building because, unlike normal buildings, it has an exoskeleton with 58 vertical columns on the outside to maximize the amount of space you can have on each floor of the building. These 58 columns converge to 28 columns at the base and at the top. There's a lot of complexity here. This isn't just about looking at a beautiful render. This is the actual design of the building. So with our new tooling, we created a portal to go from Rhino into Omniverse plugin. So let's take a look at what it looks like when we go into Omniverse. A typical workflow for architects earlier on in the design is to create a foam model that's usually on a tabletop where they can take a look at what the building will look like without being distracted by all the materials and those details. Architects like to see it in context of what it'll look like in the city. And this is Shenzhen Bay over here with the building placed accurately around the other buildings. But one thing we can do inside this virtual world that you can't do in a real world is simulate what the sun will do in terms of shadows and lighting. We can do that here inside our tool, and we can do it in real time. Change the time of day and match exactly where the sun's placement will be at this time of year relative to the buildings at that latitude and longitude.
Now, first of all, Rev, we'll just go quickly. Until Omniverse came about, this tool, Rhino, and this tool weren't able to communicate. And so now they're able to communicate through this portal that both of them has created into Omniverse. The second is the ray tracing, global illumination is done completely in real time. And so you probably noticed the beautiful shadows that are being casted. The shadows and the indirect lighting that's happening is all completely done in real time. Otherwise, this would have taken hours to render each frame. And that's the reason why people made clay models or foam models.
All right, so let's go to some beauty shots of what the building looks like after we apply the materials and go to the next stage of design.
So you might have thought that last scene was actually a photograph or a pre-rendered image. In fact, just now you saw Rev make the move. This is completely done in real time. Let's show them some more other shots.
Let's take a few more.
Everything in here is done in real time. Every single scene. All Rev is doing is changing the camera angle inside that world.
And we can also change the light source and change the sun in real time.
And the last one, you probably noticed the flowers look like flowers because the flowers have subsurface scattering. Look at the beautiful surfaces. Isn't that amazing?
One more.
Everything was done in real time. It was rendered on 8 GPUs. On just 8 GPUs, rendering this entire scene in real time, and Rev was able to change the camera angles anywhere inside that scene, and it instantaneously recreates that photoreal image. Now, designers and architects could enjoy their building before they build it and know exactly what it looks like, exactly how it feels. Now, Omniverse makes all of this possible. Hey, thanks a lot, guys. That was great. So what you were seeing were the different applications. It was portaled into Omniverse, this other universe that is shared by all of the users, different designers of different tools and in different locations if they like. And they see one viewport. That viewport could be streamed to any device. It could be streamed remotely to a Chromebook or a MacBook or a PC or a laptop or a phone. Doesn't matter where it is. It could stream it to you. As a result, everybody can enjoy the ground truth, what it looks like, in exactly the same way and from anywhere. Okay? Omniverse. Ladies and gentlemen, this is Omniverse for AEC. Early access is available now. The enthusiasm all over the industry is just incredible. Thank you very much, guys. We want to put rendering everywhere. We, of course, would like to make the computers faster themselves. But one of the best things ever is cloud computing. Anybody with just a small budget can have an opportunity to enjoy what a supercomputer can do in the cloud. Here in China, the single largest cloud rendering platform is called Ray Vision. Ray Vision renders for 85% of the studios and designers here in China. The top 3 movies were made with Ray Vision. This is a gigantic rendering cloud. Ladies and gentlemen, today we're announcing that Ray Vision has adopted NVIDIA RTX so that they could accelerate cloud rendering in the cloud for all the designers here in China. Now let me show you the amazing results. In the end, what a developer, what a creator wants is to be able to create their art as cost effectively as possible. This is a comparison between running the rendering on the CPU or accelerating the rendering on NVIDIA RTX GPUs. Look at that, 485 hours for a sequence of shots costing $310 to 39 hours and just $40. Unbelievable. From 3 weeks to just a couple of days, 1/7 the cost. You guys have heard me say this before. The more you buy, the more you save. That's right. That's right. The more you buy, the more you save. And that is the perfect example of that. Okay, so rendering in the cloud. That was the first chapter. RTX, games, rendering, creatives, Omniverse. Let me change pace now and talk to you about the second chapter, high-performance computing. I want to talk to you about high-performance computing from the context of a few new applications that weren't possible before. Something that you probably not experienced before. And so the first thing is this. Of course, simulation is possible. NASA and NVIDIA have been working together on simulating their Mars lander. By the end of 2030, NASA will send astronauts to Mars. 6 astronauts will be inside a lander, and this lander is about the size of a condominium. So imagine we're going to put 6 astronauts in a condominium, fire them into Mars, into space, and have them land on Mars. When they come to Mars, they will be traveling at 12,000 kilometers per second. 12,000 kilometers, well, per hour. 12,000 kilometers per hour. They're going to be moving incredibly fast. As they enter that low atmosphere, which is just a fraction of Earth, the amount of propulsion necessary to stop it in time, to stop it within just 6 minutes so that it could land safely on the surface of Mars is incredible. It has to fire the retro rockets at exactly the right time, exactly the right angle, exactly the right intensity. And so we've been working with them on simulating hundreds of thousands of these simulations, fluid dynamic simulations, so that they could experiment and imagine what it's like and design their propulsion system, design their lander, design their landing algorithm so that they could safely land these astronauts. However, the simulation result generates tons of data, about 150 terabytes of data. 150 terabytes of data. Now the question is, what are you going to do with that data? And how do they analyze it? And so we created a platform based on our DGX, a brand new software stack we call Magnum IO for being able to stream very high data rate from storage we call GPU direct storage, connected to a whole bunch of Mellanox NICs, and rendering on top of a software stack called NVIDIA Index, distributed volumetric rendering software. So all of that technology, the DGX, Index, Magnum IO, the Mellanox NICs, directly connected to DDN storage, is going to make what you're about to see possible. It looks like a movie because it is a movie, but it is completely rendered in real time. Ladies and gentlemen, let's take a look at landing on Mars. Everything you saw was simulated. Everything you saw was simulated. There was no art. All of that is fluid dynamic simulation, 150 terabytes of data. Now you can fly through it with a supercomputer. The first application I want to tell you is basically that HPC will be used for analytics in the future. Whether it's for scientific simulation, because you create so much data, or it's for data science, you have so much data to analyze, you need a supercomputer to analyze that. The first is high-performance computing for data analytics. Second, we've been so interested in this field for so long. Whole genome sequencing. The ability to analyze completely the human genome. The benefit of that is you could predict as a result alterations in your DNA, and to find early on potential inherited disorders or cancer mutations that are causing its progression or discovering a widespread disease. The ability to sequence the human genome in totality is incredibly powerful. This could be used, of course, to enhance our understanding of life, improve our health, but also in agriculture and livestock, so that we could protect livestock and enjoy better vegetables and farms that produce more effectively. There are so many applications for whole genome sequencing, WGS. The breakthrough that makes it possible are recent advances in NGS, what they call next generation sequencing machines, and one of which is the BGI Life Science Supercomputer. It is able to sequence 60 whole genome sequences per day. What used to just recently took 15 years to do the first human genome and still millions of dollars a decade ago, it is now possible with the BGI Life Science Supercomputer to sequence 60 genomes per day, 16 whole genomes per day. In order to sequence and understand the human DNA, the first step is to do that. And it generates a whole bunch of small fragments of your DNA. These little small fragments is called short reads. These short reads have to be reassembled into your genome. The way they do that is they compare it to a reference. They compare these little tiny short segments to a reference, and they figure out which one of the segments go in front of the which ones connect. So they reassemble and reconstruct your genome from all these little tiny fragments, comparing it to a reference. And then, most important thing, the goal is for them to do what is called call variant, to identify variations. The identification of variations allows us to detect, as I mentioned earlier mutation, potentially cancer-developing cells, or that you might have a disorder that was inherited from your parents. And so that reconstruction process, genomics analytics, is done with a toolkit called GATK, Genomics Analytics Toolkit. That's the industry standard. It was created at Broad Institute. It is used all over the world. It is incredibly computationally intensive, as you can imagine, because the human genome has 3 billion base pairs. It's like a sentence that with 3 billion characters inside. Okay, so this is a very large book. Each one of us has a very large book that encodes our DNA. And that human genome, 3 billion base pairs, comes in a bunch of little tiny fragments that we now have to figure out exactly how they're ordered and whether there are potential variances. GATK is the toolkit that is used to do that. It's incredibly CPU intensive. In fact, it takes about 30 hours. It runs on one node of computer. It's not very scalable. GATK runs on one node of computer. It takes 30 hours, a day and a half, to go and compute one of the 60 genomes that are being generated and sequenced by the BGI Life Science Supercomputer. Once that is done, petabytes of data are going to be used to analyze what's going on. This is a classic machine learning problem. In fact, bioinformatics was one of the first industries to start to use machine learning. Before there was Python, their data science language is called R, and they used machine learning to go find clusters and irregularities, deviations, and so on. Terabytes and terabytes, petabytes and petabytes of data are being analyzed to find anomalies. This is the 3 stages of what is called bioinformatics. From gene sequencing, using a next-generation sequencing machine that goes into a genomics analysis toolkit so that you could sequence the whole human genome, to create data that you can compare against all of the other previously sequenced genomes, represents the bioinformatics pipeline. This is one of the most important workflows in the world, as you can imagine why. And so we have dedicated ourselves to find a way to make this more productive. Now, one of the things that you already know is we're working on machine learning. And so all of the work that we're doing with RAPIDS that I talked to you guys before, RAPIDS, high-speed accelerated data sciences of large data. this is going to go directly into helping them here. However, one of the areas we have to dedicate ourselves is the genomics analytics pipeline, GATK. We've been working with a small company called Parabricks. Parabricks are amazing scientists that focuses in this space. And they created a toolkit they call Parabricks, and it accelerates GATK, this industry standard, and produces precisely the same answers. Their work and our work with them was so exciting that we decided to join forces and have Parabricks join us, and for us to really double down and put this technology in the hands of every single genomicist and genomics scientist in the world. So ladies and gentlemen, today we're announcing that NVIDIA Parabricks, our genomics analytics toolkit, is available to everybody. Parabricks, the software, the pipeline, is available on NGC. It's accelerated. With acceleration, you could imagine the speed up 30 to 50 times. So instead of a server and rendering it for 30 hours while the sequencing machine is generating it at 60 per day, now we could keep up with the data rate of the BGI life science supercomputer. Now this is such an important first step because in the future, we're going to sequence more and more people. And the reason for that is this. We've discovered that every human is not exactly the same. And based on our ethnicity, based on where we grew up, different regions, there are different standards and different references. Using one common reference for all human is not accurate enough and not sufficient. So we're going to create many more references. We're going to make it possible so that we could, of course, compare against all those references and find and do variant calling against all the references. So the amount of computation for genomics is going to go up. And, of course, we would like to do it more frequently. Okay? And so this is an area that is really, really important, and I'm super excited about that. This year, if I didn't include the first application for HPC that I mentioned earlier, which is ray tracing, we added 2 new applications to the NVIDIA CUDA stack, and 2 applications that are of extraordinary importance to the future of society. The first, of course, is BGI. BGI using our Parabricks stack for genomics analysis, but the other I announced several months ago, NVIDIA's CUDA is now able to process very large-scale 5G. And the first user of our platform, we call Ariel, is Ericsson. And so it is very sensible to all of the computer scientists in the room that NVIDIA CUDA should be good at the radio, the virtual radio, virtualizing the radio and running it completely in a software stack. Now we could put that virtual radio inside a data center instead of the edge and have it be much more flexible in adapting to the different traffic patterns that changes over time, and also to be able to layer on and add AI functionality that was impossible in the past. Could you imagine if we could use AI to optimize for traffic and the patterns and adjust the beams in real time so that the amount of energy that's used for 5G could be reduced, the bandwidth can go up, the quality of service could go up. All of those benefits are possible. 2 brand new applications that brings the NVIDIA accelerated computing into 2 new industries. One, telecommunication, and then the other, genomics. Thank you very much. ARM, the most pervasive CPU in the world. 150 billion shipped. Almost everybody in the world has an ARM processor. 1,700 licensees. 95% of the world's custom SoCs are based on ARM. It is the most configurable CPU core and CPU ISA we have in the world. It is therefore sensible to see so many industries and so many countries and so many companies building ARM servers. 2 reasons for that. The first reason, of course, is that high-performance computing requires very good energy efficiency, very good power. And so we could scale it up into a gigantic machine. Energy efficiency is vital to high-performance computing. And second, because the world is moving to the cloud, hyperscale is completely open sourced. Hyperscale is a brand new stack anyways, and hyperscale does not care about the CPU ISA. And that's the reason why you see hyperscalers and supercomputers adopting and creating custom ARM CPUs. These custom ARM CPUs allows them to change the ratio of cores to memory bandwidth to I/O bandwidth, and as a result, solve a whole lot of problems that a single CPU cannot. You see all kinds of amazing CPUs. Ampere is building a CPU they call eMag. Amazon recently announced Graviton 2, really exciting looking CPU. Marvell's Thunder X2, Fujitsu, the most energy efficient supercomputer in the world. Number 1 is Fujitsu. We're number 2, but they're number 1. Fujitsu with their ARM A64FX, and Huawei with their Kompong 920. That's dedicated to edge computing as well as hyperscale and AI. All of these processors are super exciting, and the industry has been crying out to us and asking us, is it possible for us to accelerate all of these processors? Because as you know, acceleration is vital to the future of computing. And so this year, we announced just a few months ago that we're bringing CUDA to ARM, and to fill that hole so that we could enable ARM to be a fantastic platform for high-performance computing as well as AI. And so this is our ARM reference system. Our ARM reference system has 2 external PCI Express connectors, and it goes every 2 CPUs connected to 4 GPUs. The reference system is based on Marvell's Thunder X2. And in just a few short months, look at the ecosystem, all the tools, and all the amazing applications that are now running on ARM. We have molecular dynamics, we have quantum chemistry, fluid dynamics, finite element analysis. We have computer graphics, we have ray tracing. Let me show you one of them. This application is the simulation result of NAMD. NAMD is a molecular dynamics simulation. After you're done understanding the molecular machine, so that you can at the simulation level understand this biomechanical machine, you want to visualize it. Essentially, this application is called VMD, Visualization of Molecular Dynamics. VMD is essentially a computational microscope. And you could look under this computational microscope and understand how molecular biological machines function. And so you simulate, and then you put that simulation result in essentially another supercomputer, and you use VMD to visually understand it. On top of VMD is made possible with 2 applications, 2 libraries from NVIDIA. One of them is called optics, and the other is streaming. Our ability to capture, encode, and remote that computer graphics makes what you're about to see possible. So VMD is a vitally important tool, and let me show it to you now.
So we are looking at a live ray tracing of the Rift Valley fever virus running in VMD on an ARM-based computer. This virus is a biosafety level 3 pathogen, and it's fatal to approximately 20% of the infected people. The problem is that we don't have a vaccine yet, and to design vaccines, it is important to understand the structure of the viral proteins. Professor Lee from Tsinghua University managed to solve the structure of the virus, so this can potentially help a lot of people in the future. And the data set to solve the structure we are seeing here was about 50 terabytes large, and it took 1 week to process with NVIDIA Tesla V100 GPUs, and they probably couldn't have done it without it.
This is really fantastic. Let's thank Professor Lee and the Tsinghua University for helping us demonstrate this incredible capability, and also thanking them for the important work that they're doing. Guys, thank you. NAMD, VMD, on CUDA, on ARM. The single most important application in the world, HPC application in the world, unquestionably is TensorFlow. TensorFlow is being used, of course, for machine learning and artificial intelligence, but it's used for scientific computing now. It's used for industries. It's used in business. This particular application and application framework, tools framework, is pervasive. Scaling up TensorFlow is a high-performance computing challenge. It is just not easy to do so. And so we've dedicated ourselves over the last, about 5-6 years, working with Google to enhance TensorFlow so that it could be accelerated to the limit. This is TensorFlow 2.0. It just came out just a couple of months ago. And ladies and gentlemen, you can now know that it runs on CUDA on ARM, and the performance at scale is very close to the state of the art. This says something about the power of CUDA and the power of factorizing all of this software so that it could be accelerated. This runs on a multi-GPU configuration and a multi-node. The entire stack is identical to the stack that we use on x86, and the performance is fantastic. I want to thank the folks at Google for working with us on TensorFlow and all the people that worked with us on making CUDA on ARM possible. Thank you. Let's talk about artificial intelligence. In 2012, the confluence of several factors kicked off modern AI. The overwhelming abundance of data, and some researchers using our GPUs to run deep learning, these new algorithms that automatically detect features. And because of its deep structure, can hierarchically learn the representation of knowledge so that it could be generalized. The effectiveness of deep learning has been extraordinary. The confluence of these three factors, big data, deep learning, and NVIDIA GPUs, kick-started modern AI. Since then, amazing things have happened. We've seen in just a few years' time the achievement of superhuman levels of image recognition, superhuman levels of speech recognition, and now some very important breakthroughs in natural language understanding. When you look back on 2012, and it was just this incredible breakthrough we call deep learning and the winning of ImageNet, almost no one realized the potential impact of that moment on the industries around it. ImageNet, or AlexNet in 2012 really kickstarted innovations in so many different industries as a result of computer vision finally being solved. It's not completely solved, of course, but computer vision has achieved incredible results, as I mentioned earlier, superhuman levels. That moment has made it possible for us to have kickstarted the self-driving car revolution and all the work that's happening. It has kickstarted amazing photographs to be taken on phones to the point where you can now take pictures in the dark. You can now have radiologists be able to use AI to detect disease. The number of applications, the number of industries, manufacturing robots are now going to be advanced. The number of industries that will be affected is truly daunting. All started as a result of ImageNet. Last year, something very important, equally important, happened. And arguably long-term will be even more important, which is the creation of BERT. This natural language model that is pre-trained on a large corpus of information and somehow understood by looking at all of this data in Wikipedia, all of this text, all these stories, all of these sentences, it learned the structure of language. BERT, just as ImageNet has decoded computer vision, BERT is in the process of decoding the code of human knowledge. Natural language is the way that we communicate and we transmit knowledge to each other. We encode it to protect it, to remember it. We encode it to transmit it and share it. Language is the code of knowledge. And now with BERT, we have decoded the code of knowledge. Understanding the code of knowledge as if H.264 or JPEG, or understanding that code unleashes all kinds of incredible innovations. We're going to find in the next several years the ability to do some amazing things in the way that we deal with text and the way we deal with language. At the core of what makes that possible, of course, is the engine of learning from large data. In the last several years, in the last 5 years, we have accelerated training of deep learning by 300 times. Just think about that. In 5 years, Moore's law in 5 years is 10x. We've accelerated training by 300 times, and the ability to train large models tremendously. We did so by innovating at every single level, as I mentioned earlier. From the GPU architecture, V100, inventing the brand new Tensor Core, the CoWoS packaging system, where chips are layered on top of chips and wafers, the 3D packaging of memories, the use of high-speed memory called HBM, connecting all these GPUs together into a super high-speed link we call NVLink, creating a system we call DGX, all of that so that deep learning researchers can continue to explore the boundaries, to explore the limits of what's possible with AI. It is the #1 fastest computer on MLPerf challenge 2 years in a row. This engine has really helped researchers all over the world. And it happened just in time. If you take a look at what's happening, notice what's happened. Everything was moving along just fine, and computing levels was moving at traditional rates, and all of a sudden, the emergence of deep learning, learning from all of this data, computers that write software by itself, computers that learn automatically important features and patterns from a large amount of data, all of a sudden emerged, and it caused computers to skyrocket. The computer workload rising quickly makes sense, and the reason for that is this. If you say to yourself that AI is about machines, computers, and software that learns to write software by itself, why wouldn't you want the world's fastest computers to write the world's best software? And so the number of HPC installations around the world has really skyrocketed in just the last several years. And now performance requirement, this is workload, computational workload, is doubling every 3.5 months. This trend is likely to continue. And the reason for that is because one of the areas that we would like to explore is multi-modality learning. To be able to take different modes of information, combine it together, and learn from it, find patterns across different modes of information, whether it's sight, vision, and language, video and language, images and language, previous text, your history and language, all kinds of different areas could be mixed together for us to learn patterns and connections from. Our AI journey starts with the creation of the platform for training models. DGX is our training system. This is the beginning of the journey. The most important journey, of course, is applying AI. Applying AI. And so the question is, how do we apply AI and bring this capability to the world? The first step is sensible. It should be in the cloud. The availability of data, the type of services are simply not possible without AI, without machine learning. And so our first journey was cloud. The platform we call for cloud computing is hyperscale, and therefore HGX. DGX was our deep learning GPU accelerator. DGX was designed for training. HGX is designed for cloud. EGX is the next stop of our journey. As we move AI closer to where the action is, we call that edge, and that system is called EGX. And eventually, we would like to bring AI all the way out to the world where the AIs are autonomous and moving among us. That system and that platform is called AGX. AGX for autonomous or robotics, EGX for edge, HGX for cloud, DGX for training. One architecture, but the software stack and the computing stack completely different. And the reason for that is very obvious, because each one of these computing platforms, whether it's autonomous at the end or in the cloud, have very different capabilities and requirements. The way you manage, the way you operate, its form factor, all different. And so This represents the taxonomy, the language, if you will, the mile markers of the rest of my talk with you. I'm going to talk to you from this side to that side. We have now in the AI chapter, the first section we've already talked about. I've got 3 things I want to talk to you about. The first is the single most important AI model on the internet. This is my schematic of the single most important AI model of the internet. Without this model, it is impossible for us to enjoy the internet. And the reason for that is this. The internet gave us access to the world's information. Unfortunately, the world has a lot of information. The amount of data that's out there, it's trillions of web indices, hundreds of billions of TikTok videos. I think it's hundreds of billions, right? Billions of products on Taobao. News in the millions. Books in the millions. Movies in the millions. The era of search has ended. If I put 1 trillion things, 1 billion things, 1 million things, and it's changing all the time, how can you possibly find anything? The era of search is over. The era of recommendation is here. Everything has to be recommended. Of course, the internet companies have known this for some time. It started with, of course, different and much more simple versions of recommendation systems using matrix factorization, whether it's collaborative filtering or content filtering. Most of those applications were light on computing, but it had limited capabilities. It didn't have the ability to understand, for example, information that are unstructured. For example, it takes deep learning to understand information that's unstructured. It has limitations on how far or how big of a corpus it can learn from, how big of a directory it can learn from, how big of a database it could learn from. This is a block diagram of a, if you will, canonical recommendation system. The most important thing is this. There are users and items, users and items. We have 6 billion users in the world. There are tons of items. As I mentioned, 2 billion products in just Taobao alone. There's all kinds of movies and social videos and websites and stories and books, and every single one of those items is something that we're interested in. It is in the trillions. There are billions of people, there are trillions of choices. Somehow we have to find something we like. Somehow we have to find something that makes sense to us. How do you solve this computer science problem? Well, recommendation systems is the way that it's done. On this side, ultimately, are billions and billions of choices. And it has to go through a candidate generation system. It's a filtering system to go from billions to hundreds. From that hundreds, this is the most important part, it has to figure out how to rank it to you. The way it ranks it to you depends a lot on your what is called implied preferences. It has to learn your implied preferences. What do you like? And from that implied preference that it learns, it will rank order this list and present to you a few choices. From billions and trillions of items, and changing over time to just a few recommendations. It could recommend to you news, it could recommend to you books, it could recommend to you food, restaurants you should go to, recommend products, recommend videos you should enjoy, that you will likely enjoy, tweets that you want to read, so many things that it could recommend. The recommendation system is extraordinary. As I mentioned, it used to be based on CPU-based collaborative filtering techniques and content filtering techniques, but now the industry is moving to deep learning. Moving to deep learning has all the benefits of being able to learn preferences from unstructured data, the ability to scale to a much, much larger system. However, the processing time is also much more intensive. There's a couple of things that has to happen. The input are the billions of dimensions that I mentioned. the billions and billions of dimensions. Billions of people, billions of things. That is extremely high dimensionality. It goes through this concept called embedding, kind of like word-to-vec embedding, which takes a high dimensionality, reduces the dimensionality. From that dimensionality of embedded items and users, we could learn information, learn relationships and interactions and connections associated with those embeddings. It is the reason why king minus man is equal to queen. It is the reason why pear apple minus apple is equal to pear. Those embedding systems allow these relationships to be learned. The embedding system and the ranking system is learned together using deep learning. It is incredibly computationally intensive, as you could imagine. This recommendation system that used to be based on CPUs are now moving to GPUs. And that is a really, really important moment. So Baidu, they want to go to deep learning. And they want to create this new thing called AI Box. And it's based on wide and deep. It takes wide vectors, really super sparse entries that are because of human known preferences. We know that people have these preferences. And so we don't need deep learning to do it. And that sparse table is billions wide, 100 billion wide. Dimensionality is very, very large. The sparsity is very, very high. On the other hand, they have the embedding table 10 terabytes large. Together, between that wide and deep, they have to train this ranking system, this ranking model. Well, it turns out 100 billion dimensionality, a dimension of 100 billion, and a 10 terabyte embeddings table is simply impossible to do cost effectively on CPUs. And so we worked together to move it on GPUs, and they were able to reduce the training time and reduce the cost by 90%, just 1/10 of the cost. Just 1/10 of the cost. As a result, of course, they could reduce their cost, but very importantly, they have so many models they have to train, and they would like to move all of them to deep learning. Hundreds of models, from products to news to websites to banners, all kinds of models has to be developed for deep learning. And so this is really a great achievement. Their poster is outside, their researchers outside, and they'd love to talk to you more about it. And it solves this problem of taking enormous amounts of data that's available on the internet, too many choices, to filter it through the recommendation system so that you only see 10. How do you take this massive amount of data, hundreds of billions of large in dimensionality, and in the future, trillions large in dimensionality, and reduce it to just 10 items? That's, frankly, a bit of a miracle. And this is the miracle of deep learning. This is the miracle of AI. And Baidu calls it AI Box, and the results are really fantastic. And the thing I would like to say is that because of the incredible reduction in cost, the more you buy, the more you save. Chinese people love saving money, right? I love saving money. It makes me so happy. Speaking of saving money, Alibaba's recommendation system, also powered by NVIDIA. You guys know Alibaba, Singles Day, the single largest e-commerce event, the single largest shopping event in the world, in the universe, in the galaxy. It is impossible what happens here in China on Singles Day. Why are there so many singles people? $2 billion products, 500 million shoppers on one day. 1.5 times the size of the United States. Everybody shopping. Who is working? Everybody shopping. 500 million people shopping on one day, trying to decide which one of the 2 billion products to choose from. Billions of queries per second. Now, one of the things that I mentioned earlier is, of course, this model, this recommendation system, is fairly universal. This is a canonical architecture. It's fairly universal. And this universal architecture has all kinds of different algorithms and different architectures, and there are lots of different ways to refactor it, but basically the concept is the same. And to be able to filter all those choices down to just a few, and to do it with deep learning, the computational load for deep learning was too high for CPUs. When they moved to deep learning, the effectiveness was higher. Their click-through rate was higher. And you know that click-through rate in e-commerce and internet directly contributes to the success of the commerce. And so click-through rate absolutely improved. However, the computation time also improved. Using a CPU, Alibaba's model could only do 3 queries per second. 3 queries per second. I mentioned earlier that there are billions of queries per second. These 500 million shoppers and all the people that interacted with Alibaba but did not shop created a lot of queries. Those queries has to be responded quickly and cost effectively. If it can only query 3 queries per second with one CPU, and there are billions of queries per second, how many CPUs do you need? The entire world CPU is not enough. And so therefore, we work together to accelerate their deep learning model on our GPUs. That is the power of deep recommender systems. Deep recommender systems, unlike traditional collaborative filtering or content filtering, matrix factorization, was very good for CPUs, but unfortunately, it wasn't very good for GPUs. Deep recommenders are more accurate, can handle unstructured data. The features of your implied preferences could include a lot more things. The size of the data could be much larger, and it can be GPU accelerated. Whereas the CPU could do 3 queries per second, a T4 GPU can do 780. 780 versus 3. Very big difference. This is the perfect example of the more you buy, the more you save. Perfect example. This also is very interesting. This is one of our brilliant data scientists, and this is what Taobao recommended to him. This music player called Abaso, and the world's largest hamburger. He must be very, very hungry. Incredible. All right. So, number one thing I want to say is deep learning inference is wonderful for deep recommender systems, and the recommendation system, the recommender, is the engine of the internet. Everything that we do in the future, well, everything that we do now, passes through a recommendation system, and it's going to be based on deep learning in the future. One of the most important tools that we create is called TensorRT. TensorRT is a computation graph compiler and optimizer for CUDA GPUs. It takes the output of TensorFlow, and it goes through and finds optimizations, nodes and edges that can be optimized, shared, fused, and generates optimized CUDA code to run on any of our GPUs. TensorRT makes it possible for us to not only train with TensorFlow, but to take the output of TensorFlow to run in a very fast way on GPUs. TensorRT is very important. Last year, we announced here in China TensorRT 5. TensorRT 5 has the ability to handle CNNs, fuse horizontally in the same layer in the same layer of the graph to be able to fuse horizontally different nodes, combine nodes and edges. It could fuse vertically. It has the ability to automatically detect places where it could reduce the precision of the mathematics and use different parts of our Tensor Core GPU, FP32, FP16, or Int8, to accelerate the deep neural network runtime while reducing power and not sacrifice accuracy. That entire loop was made available last year. That's called TRT5. It has 30 different optimizations and transforms that it does. Unfortunately, as you know, some of the most important applications are not CNNs, but they're based on RNNs. CNNs is a feed-forward network. Data propagates forward in the network. RNNs is complicated. RNNs is a feedback network. State of the past, previous state, previous memory, along with current data, affects the next output. It's a state machine. RNNs is a feedback network and supremely complicated. Well, ladies and gentlemen, I'm really excited to announce something that's really, really important, and it's probably one of our greatest achievements, TensorRT 7. TensorRT 7 TensorRT 7 has the ability to handle CNNs, of course, but also transformers, RNNs, autoencoders, which are versions of CNNs, and be able to do that automatically. Whether it's all of the different configurations of RNNs that needs to be generated, the first thing it does is it does code generation, kernel generation, automatic kernel generation, so that there are mathematic kernels that has to be generated for CUDA that wasn't possible to have pre-described. Because RNNs have so many different configurations. They have so many different activation functions. There's so many different ways you could remember the past. The state machine is very complicated. We fuse horizontally wherever we can. We fuse vertically wherever we can. We auto-generate code for all of the custom kernels of RNN. We even fuse over time. We look for opportunities in the processing pipeline over a period of time to find ways to share the computation, to reduce the amount of processing load on memory, to reduce the amount of traffic, fuse over time. And then lastly, of course, we still automatically detect all the different areas where we could reduce complexity, reduce precision, while continue to keep the accuracy. If you look at the number of models that we support, last year we supported basically ResNet 50 and SSD and all the other versions of CNNs. Those two versions, those two networks were, these are the top networks being used in the world, the types of networks that people use. Those two were the only ones that were supported by TensorRT 5.0. And all of a sudden, this year with TensorRT 7.0, automatically it will compile and optimize for all versions, all varieties of RNNs and LSTMs, transformers of all kinds. And in fact, the most important neural networks of our time today. It has thousands, over 1,000 different ways of optimizing kernels and fusing operations, from 30 to over 1,000. And so TensorRT 7.0 is available now. I think it's going to be put up on NGC in the near future, and then you'll be able to develop the networks that you would like. It would take the computational graph and optimize it into a CUDA runtime. And you can get the benefit of really, really fast inference. Ladies and gentlemen, TensorRT 7.0. So what can you do with TRT 7? What can you do that you could not do before? Well, of course, you could do them slowly. Of course, you could do it with more cost. But there are some things you simply cannot do if you don't accelerate the entire pipeline of neural networks. One of them is one of the most important developments in AI today, conversational AI. Several breakthroughs have made conversational AI possible for the very first time. The ability to do speech recognition at a superhuman level. Natural language understanding models that correct what it heard wrong so that the precision is really, really high. To have the ability to understand your intention, make recommendations, do various searches and queries for you, then come back, summarize what they learned, the AI learned, into a text-to-speech system, and then to synthesize the voice in a very natural and happy way. That loop is now possible. It takes 20 to 30 models to make this possible. However, all of the technology are now in place. The challenge, of course, is that it is too slow. Conversational speed is, of course, real time. And if you ask a question and it doesn't respond fast enough, if you have to wait several seconds, it seems like the individual, the person, is not even interacting with you. Low latency computing is really, really vital. And we now have achieved with TensorRT 7 the ability to compile and optimize every one of those networks from end to end, and to do it in 300 milliseconds. It is now possible to achieve very natural, very rich conversational AI in real time. Okay, so this is what TensorRT 7 can do. Thank you. Since last year, our journey of TRT has really made progress. Since last year, our journey to accelerate inference has made enormous progress. We postulated, when I stood here in front of you last year, I said that inference is a super complicated problem. And the reason for that is very obvious. Inference starts with many, many people developing very complicated software. And this complicated software is written by a computer. And that computer is gigantic. That gigantic computer is generating very complex computational graphs, the largest the world's ever seen. Somehow, we have to have another program understand that graph, optimize that graph, and target it into a computer so that it could run at very high speeds. At very high speeds so that it could be deployed largely, broadly, at very low cost. The targeting of that generic computational graph, which is already very complicated and made complicated by RNNs and feedbacks, to be able to target that into a machine is really quite a technology undertaking. And that's the reason why I've always felt that inference was going to be a great challenge. There's another reason why inference is a great challenge. The rate of innovation and the number of ideas that people are coming up with in deep learning is growing, not slowing. It's growing, not slowing. And so therefore, the number of architecture and number of ideas, like BERT, are growing, not slowing. It is impossible to know. It is impossible to know whether a computer will be ideal for inference unless you knew that it was ideal for training. If you can learn on the computer, of course, it will run on that computer someday. And so one of the benefits, one of the reasons why I felt so strongly that this is an area where NVIDIA should put our energy in is because inference needs to be future-proof. The number of data centers all over the world, tens and tens of millions of GPUs or CPUs, we need to know that that body of computers will be compatible and optimal for software that's going to be written 3 years from now, 4 years from now. It has to be future-proof. Well, one of the great things about CUDA is that it is future-proof. We are in CUDA 10. CUDA 10 is compatible with CUDA applications written today. It's compatible with architectures we've shipped long ago. The NVIDIA CUDA is future-proof. Applications can continue to grow on top, and we will continue to optimize software, develop software that will run wonderfully on the install base years from now. And as a result, one by one, as all of the internet companies in China moves towards using deep learning and recognize the power of conversational systems, natural language systems, and recommendation systems. We've seen enormous success here. So I want to thank all of our partners here and all that worked with us to make this possible. Thank you. Very quickly, we have enjoyed, our industry has enjoyed the AI moment. Two things made it possible: the smartphone and the cloud. The smartphone and the cloud has made it possible for the iPhone moment, the smartphone moment, to have made it possible for the industry to be completely reshaped and society be completely reshaped. Well, it is time now that every industry is going to enjoy the smartphone moment. We're going to see the smart everything moment. Everything will be smart in the future. And the reason for that is because sensors will be connected to everything, some people call IoT. And that sensor information will be streamed, and it will be processed by AI to recognize automatically patterns, changes, and to reason about what action should be taken and take it. We are going to automate everything. Automation is going to be one of the great forces that are going to make each and every industry more productive. The automation of everything, smart everything revolution. That AI cannot run in the cloud. That AI has to run at the edge, at the point of the action. The reason why it can't run in the cloud is because sensor data is being streamed continuously 24/7. These sensors, many of them are going to be high-resolution sensors. They could be cameras, they could be LiDARs, they could be radars, imaging radars, they could be all kinds of infrared cameras. They're going to be streaming continuously from everywhere. It is not possible to stream all of that data to the cloud. Second, the latency of traveling to the cloud and processing and back is too long. It is impossible to have a robot that is working with you, responding to you, and the processing done far away. The latency is simply too long. And then lastly, data sovereignty and data ownership cannot be guaranteed in the cloud. Sometimes you don't want to put private data in the cloud. And so there's a lot of reasons why we want to put intelligence at the edge. We call that system EGX. We started working on EGX a few years ago, and the momentum has been fantastic. We now realize there are so many different applications far beyond our dreams. And every single industry has the benefit of now applying AI to automate their industry. Whether it's in healthcare, a third of the world's population are elderly. They should be monitored and watched all the time to make sure that if they fall, if something were to happen to them, we can send help right away. 570 million farms in the world. There's no way to have people monitor all of that. We put sensors everywhere. 2 million factories will be automated. 13 million stores. $27 trillion industry has the opportunity to be automated and to make more productive and more profitable. The universal translator call centers that understands every single language. There's so many different applications. Smart cities, more convenient airports. All of these different places has an opportunity to be automated. We call that intelligence at the edge, and the computing platform is called EGX. We've seen incredible success. EGX, recently, let me tell you about a couple of them. One of them is Walmart has put into all of their stores, they're deploying into their stores smart retailer systems, smart checkout systems, make it much more productive. If they could save just a few dollars, a few small percentage of a $27 trillion industry, the return's fantastic. United States Postal Service, 500 million mail pieces per day. And using computer vision at a very large scale and very high rate, streaming, basically it's almost like streaming AI, we can now help them do a much better job with sorting mail. All kinds of interesting applications. And one application that I'm very excited about is the ability to put our GPU into the fabric of wireless communications so that AI can also run not just on internet, but also on the on the telco networks. Okay, so the work that we're doing with Ericsson is really important. Let me now talk about robotics. Robotics is a special type of computing. Robotics, autonomous systems, has to basically do three things. we all basically do three things. We sense the environment. We reason about, we might reconstruct the environment in our mind. We reason about the environment. We reason about the environment relative to our goals, and then we plan action. Sense, reason, plan. That loop is continuous in intelligent systems. We would like to put that loop, that high-performance, real-time computing loop of sensors and reasoning and planning right at the edge so that robotics will be possible. We called this basic system Jetson, and we also created several applications and stacks for different types of robotics applications. One of them, the most important one in the moment, is Drive, using robotics technology to make autonomous vehicles. The second is putting AI into instruments. In the future, your medical instruments will be self-driving. Self-driving medical instruments, so that while you're taking and acquiring the sensor image, the system will help you and assist you in acquiring the proper image and acquiring the best image. The AI would then improve the image. The AI would also help in detecting disease. And so AI autonomous self-driving medical instruments, from the acquisition to the processing and the detection pipeline, really, really profound. We call that Clara. And then lastly, for robots that are maneuvering inside an unstructured world, cars can drive on lanes, but robots cannot. They have to operate in unstructured worlds or manipulators. Those robotics algorithms are different. And so we created several different stacks: Jetson for general purpose embedded, Drive for autonomous vehicles, Clara for medical instruments, and Isaac. In each one of the cases, our offering is end-to-end. Our mission is not to create self-driving cars. Our mission is to create the infrastructure, the computer, and the software so that every company in the world could build self-driving cars. We believe that everything that moves in the future will have autonomous capability. Whether it's passenger-owned vehicles or vans or trucks or shuttles or trucks or delivery bots, everything will have autonomous capability. It could be completely autonomous, or it could have us in the loop, autonomous. And the algorithms and the computing structure is basically the same. The first thing we do for self-driving cars, from the data collection, data labeling, to the training of the models, the simulation of the self-driving car, to the in-car computing platform, we create all of that. We create all of it and we operate it ourselves as if it's our car. However, we make the entire computing platform open. The software stack from the operating system to the middleware, the reference applications, and the pre-trained networks. The networks that we use to create this autonomous vehicle are all made available to our partners. From infrastructure, computing stack, as well as pre-trained networks. This is our body of work, and when we work with our partners, all of it's made possible, available to them. Today, we're announcing something that's rather new. We're going to make our pre-trained models, the models that we create, and there are tens of them. There are so many different types of models that are used in order for self-driving cars to be possible. We have been requested time and time again, because of the quality of our networks, we treat these networks as if they're industrial strength networks that we will ship and maintain for as long as we shall live. And so these models are done with extraordinary care to the highest possible quality. And their capabilities are really quite incredible. We have a lot of expertise in this area. And so our partners have asked repeatedly whether it was possible for us to share our models with them. And the answer today that I'm announcing is, from now on, it is possible for all of our partners who are using Drive to come to us, and we would share our models with them, the pre-trained models. The question is, what can they do with that? It comes with it a tool. The pre-trained models, of course, are designed and optimized for our car configuration. With the transfer learning tool, it is possible to download from NGC the NVIDIA GPU Cloud Registry. You could download these pre-trained models, and you could use the transfer learning tool to adapt it to your own configuration. You would, of course, collect your own data. We're happy to share with you our labeling system and show you the standards by which we label data. That collected data could then be used to refine, adapt our pre-trained data into a new network, which would then be optimized and compiled using TensorRT into your platform. Now, all of a sudden, if you're developing something where the sensors' location are slightly different than us, maybe you're creating a truck while we're creating a car, and maybe the camera location is slightly higher. Maybe you would like to collect data for a particular use case and region that you feel that our data collection is under-contributed. There are a lot of different reasons why you could then now take our pre-trained networks and adapt it to your car. We call it drive transfer learning. This is the first step. The really exciting stuff, the really exciting part is federated learning. We have been asked repeatedly whether it's possible to partner together where your data and your data collection and your labeling and our data collection and labeling could come together to train a common network, but we don't have to move data. Because the amount of data is so gigantic, or it might not be possible to share data, but we could share a common training of a model network. And we call this federated learning. We've now developed a system, all the infrastructure is put together. And so when you collect your data, you train it with our transfer learning tool, it is now possible for us to now return the weights, the delta weights of the network back to the master server for us to do federated averaging of all the different partners, combine that into a new network, update all of the partner networks. This has the ability to protect data, keep our privacy, reduce the amount of movement of gigantic data that will happen over time, and enable cross-company collaboration across different countries as well. Okay, so federated learning is really, really powerful. Today, I'd like to announce our next generation. Xavier was the world's first robotics processor. It was the world's first robotics processor because we designed it for one purpose. We designed it for the computing stack of real-time sensor, mapping, localization, and planning. That loop is the fundamental robotics loop. And we created a processor called Xavier for that fundamental purpose. It was the world's first SoC designed with that only application in mind. And it has been a gigantic success, and I'm so proud of it. Today, we're announcing our next generation. A giant leap forward. We call it Orin. This is the AGX Orin. It is 7 times the performance of Xavier. It is 7 times the performance of Xavier. It's 7 倍. It's 7 times. What industry from generation to generation increased performance by 7 times? The reason is because the robotic stack and self-driving cars is a very hard problem. We would like to increase the resolution of the sensors. We would like to add more sensors. We would like to increase the processing speed so that the reaction time of the cars are higher. It's very, very important. We would like to make it software defined so more software can be put onto the computer. And this is the most important part. We would like to make it safer than ever. So the amount of redundancy inside this computer is much greater. Every single CPU can lockstep with other CPUs. Every single GPU can lockstep with other GPUs. So we can run these processors concurrently, and we can check their results because they were running in lockstep. Inside Orin is a very special security processor so that all the data in motion and all the data in place are encrypted. We want to make sure that this machine is safe to cyber attacks and that it is safe to tampering. The robotic systems of the future must be safety first in mind. And so Orin was designed with these characteristics. 17 billion transistors, 12 CPU cores, 200 trillion operations per second. Xavier was 30. This is over 200. Incredible amounts of performance. This is what the Xavier stack looks like. We created one architecture that's scaled from L5 all the way down to L2, L2 all the way down to L5. One architecture, completely software defined. All the software that runs on Xavier runs on Xavier plus GPU, runs on Pegasus, which is multiple Xaviers and multiple GPUs. Some customers chose to build L2s by taking a fixed function ADAS chip and adding a CPU so that you could have lane keeping and ACC. Some customers decided to use Xavier for L2 so that you could have the ability for surround cameras and be able to do lane changes. This basic approach, this stack up, is consistent across the world. Almost everybody who's doing self-driving vehicles that are software defined are using Xavier, and then there are fixed function ADAS systems, sometimes with CPUs. Looking forward, we believe that much more people will continue to use software defined. And the reason for that is because operating a fleet of cars is like operating a fleet of phones. It is not possible to operate this fleet without the ability to have continuous CI/CD. You want to continuously enhance, you want to continuously update, and add features to the whole fleet. Fix problems as quickly as possible. CI/CD is vital to the future of IoT systems, this smart everything revolution. This stack that Orin enables essentially increases performance by a factor of 7 or performance by a factor of 4 while reducing power at the same time. One of the things that we're doing with Orin is we're creating for the first time a cost-reduced Orin, a cheaper version of Orin, so that L2 companies with just one camera and maybe surround radars could have an entry-level AV car that's also software defined. One of the things that we really love about this, and our partners love, is that the development of this system, all of the software that you develop here will carry over to Orin. As you know, everybody in the audience knows that software cost is the vast majority of the engineering cost in the future. You ship a computer once, but you maintain the software forever. You ship the computer once, but you maintain the software and enrich it with new AIs forever. This is going to happen in autonomous vehicles. The capability is so complicated, we are going to be developing software for as long as we can see. And we would like to use the same architecture so that the software can be updated across the board, across many, many years, across many, many cars in your fleet. One architecture, completely software compatible, from L2 to L5, from generation to generation. Okay, so that's Orin. Xavier was designed for the 2020 start of production cars. Orin is designed for 2022, 3 years from now, start of production cars. Today, I'm announcing a very special partner. We've been working with them for some time. We work with them across AIs as they connect customers, riders to drivers. We work with them because they're one of the world's largest AI companies. The body of work that they have to do is quite extraordinary. You know that there's a company here that connects millions and millions and millions of drivers and riders every single day. And that company is DiDi. They're the world's largest ride-hailing company. And we work with them across data analytics, across developing of AI to connect and recommend which driver could connect with which rider. And now we're working with them to bring autonomous capabilities to their fleet of cars. DiDi has selected Drive AV for their autonomous AV systems, and they're going to be testing their fleet in the near future in Shanghai. Let's welcome DiDi. Okay. The largest industry in the world, 10 trillion miles driven per year, $100 trillion industry. We believe that everything that moves will be autonomous someday, and will have autonomous capabilities someday. And the number of things that move, from cars to trucks, mobility services, there are startups that delivery vehicles. The ecosystem, in order to enable this autonomous future, is large. This is not the work of one company. This is the work of one industry. We've created an open platform so that we can all team up together to go realize this autonomous future. And so our ecosystem is really rich. You can see all the companies that are working on here, just incredible companies that are building all kinds of really innovative products and mobility, all the way from building cars to, on the other end, simulation. This rich ecosystem is really a testament to the openness of the platform, the software-defined nature of the platform, so all of these companies can innovate on top of it, and the fact that they could rely on this platform for their entire fleet as well as generations to come. And so I want to thank all of our ecosystem partners for helping us and partnering with us to realize this amazing future of autonomous transportation. Thank you. Okay, I'm going to show you a quick video. This is a video of our latest work. What you're about to see, every year when I come, I show you a quick video. This one is address to address. From a car-stopped drive across 17 miles, 3 highways, 4 interchanges with lights, autonomously, merging into traffic, changing lanes. The car had to create its own map. If a car is a great self-driving car, it's also a great mapping car. And so the first time it drove, it maps the roads. It fuses multiple drives together. And so now it remembers, I've been here before. And it's a guide to help it localize, after which it does real-time perception. All of the models that I showed you earlier is in operation. And this is captured this last week, our BB-8 driving in California.
使用手机。
What do you guys think? Open platform, BB-8 driving by itself. The car even makes sure that you're paying attention. Sophisticated AI, posture recognition, all kinds of interesting AIs that we're going to do for a cockpit, as well as the confidence view, so that the AI could show you what's in their brain. The confidence view is very, very important to give you a sense that the AI is doing the right thing. We need intelligence to give us feedback. The confidence view is what gives us feedback. So that's our latest BB-8. The platform is open, and we love all the work that we do with you guys, and I want to thank you for that. We've done the same thing for robotics. Same 3 parts. The infrastructure, the AI development infrastructure, robotics development infrastructure, the computing platform, the computer, the software stack, the algorithms, and reference applications. In the case of self-driving car, in the case of Drive AV, there's the reference application for AV, and there's the reference application for IX, Intelligent User Experience. Drive AV, Drive IX are the 2 reference applications. In the case of robotics, our 2 reference applications are Carter and Leonardo. Carter, designed for indoor navigation or navigation in unstructured worlds. Navigation in unstructured worlds. The reason why that's so different and so hard is because, well, first of all, self-driving car is very hard, but it has lanes and signs. It has lanes and signs. Inside a warehouse or inside a building, there are no lanes and signs. And so it has to navigate in a different way. How it understands where it is, mapping, localization, and path planning are different. And so Carter is the reference robotics application for indoor navigation. We also have a Leonardo reference application that's for manipulation. Manipulation, indoor navigation, recognize that these 2 applications, even the way you collect data is fundamentally different. And the reason for that is because a self-driving car's degree of freedom is basically this: forward, left, and right. And as a result, we can collect the data for lanes, signs, lights, cars, trucks, people. We can collect all that data and carefully label it. Unfortunately, for robotics, the perception has to be completely free-formed. It is impossible to collect every angle of information, to label it accordingly, so that the robots can learn perception in 6 degrees of freedom. That has to be done in simulation. As you know, NVIDIA is very good at computer graphics. And so we created a world where Isaac, the Isaac world, where robots can learn how to be robots. It learns how to recognize and perceive things in 6 dimensions. And so the ability to simulate, to train, as well as simulate to navigate, those pipelines are available on our platform. And then you could develop the software. It's designed so that it's very easy to use. And then you could create these robots yourself. If you have special needs for deep learning, we also have pre-trained models. And again, these models could be made available to you. You could use the NVIDIA Transfer Learning tool, and you could adapt it for your needs. Let me show you what our engineers did with this SDK in just a weekend. Okay, so the next video, this is how easy it is to create robots now. that cool? With the Isaac SDK, you could create all of these. And it's so simple. And of course, there's nothing easy about robotics. But the algorithms and the applications and all the technology has been encoded and embedded into the Isaac SDK. It's open to you. You're welcome to use as much or as little as you like, and to customize it and create your own networks. And hopefully together, we could create some magical, amazing robotics together. Let me show you one more thing. This next one is really quite a miracle, and it's impossible without simulation. We know that articulation, human articulation, is one of the great challenges. The ability to teach a robot and to generalize it, the important thing is to generalize it so that independent of the environment and independent of how you interact with it, it can respond to you, and that it could respond quickly and gracefully. It can respond safely. It can understand and perceive 6 dimension of freedom, 6 degree of freedom pose. It could work in 7 degrees of pose. And of course, it can interact with you, meaning that it can replan whatever it was trying to do. It could replan in just the most clever way to reach around, to interact, to back away as it interacts with you. We call this robot Leonardo, and it's the work of some amazing researchers at the NVIDIA Robotics Research Lab up in Seattle. And so to show that to us, it's its lead architect, Nathan Radcliffe. He's going to bring out, I hope, Leonardo. Hey, Nathan. Hey, guys.
Hey.
We saved the best for last. Wow. Okay. Well, first of all, Nathan, you want to say hi? Tell everybody what we're about to see.
Hey, this is a fundamentally collaborative robot. It's one of the first robots built from the ground up. The system is engineered from the ground up to be fundamentally interactive. And that's really because in the future, in the very near future, a lot of the applications that we want to do will be around people. About like 90% of the things that we would like robots to do can't be done currently because robots are so dangerous. And so we use perception here, real-time perception and real-time reactivity to make sure that they're safe and reactive and perceptive around people.
Now, Nathan, Leonardo has a RGB camera and has a depth camera.
Yeah.
And it has inside-out perception and also has outside-in perception, or just inside-out perception?
It basically has perception coming from here, perception coming from here. This kind of egocentric perception. It can see my hand, so it's always reacting to what I'm doing. It has perception from the outside, so it just kind of has a more broad perspective of what's happening. It can recognize each one of these blocks. Constantly has feedback about where it is and such.
Are you sure you didn't pre-program that? Come here. Oh, come on. It's okay. It's okay. I know I'm not Nathan. I'm not your daddy, but I'm nice. Here, I'll give you, no. How about this one? Really? Really? Wow. Well, Nathan, what else could Leonardo do?
It's going to start pushing these around, kind of clearing out the space.
So you gave it a mission.
I gave it the mission, yeah.
Yeah,
it's going to start picking these things up and just stacking them as precisely as it can. So here it's just kind of like making sure that everything is nicely organized.
And the reason for that is because Leonardo wants to stack it in that spot underneath. And so it's moving some stuff out. Mm-hmm. And so one of the things that you realize that Leonardo right now has to understand 6-degree pose. Right? So 6-degree pose, not the car, where it's looking at the world through just one angle. It's looking at the world through a lot of different angles, and the blocks are all in different orientations and different wonky shapes. And so now it has a mission that it has to now go and stack them together. And so the first thing it did was it cleared the space, just like we do. We cleared a space. It's pretty cute.
So it's taking a look at where that thing is. It recognizes what the pose is. Then it's going to go for it. It's considering. It's a little bit frightened by the audience and the bright lights.
Yeah. Uh-huh.
Come on, little
Please?
guy.
The clock is ticking.
Here. This one here.
Oh. Oh, no, do it again. Do it again.
There we go.
Wow. And so it's interesting. So remember, its eyes are very close to its hands. And so once it places something, it has to take a step back and look at the world again.
Yeah, yeah.
And so you see it do that. That's actually really interesting.
It's
it
like
wants,
sorry, go ahead.
Yeah, go ahead.
It's like it's grabbing it with its mouth, and so it comes in there, it can't really see anything, it picks it up. It's not entirely precise, but it places there, and then it pinches it and lines it.
Well, in the future, we need some separation between our hands and our eyes, right?
Yeah, yeah.
And which is kind of the reasons why this separation kind of makes sense too.
Exactly.
Yeah. Oh, wow. All right. Fantastic.
Thanks.
Congratulations. Oh, wait. First of all, Leonardo had to learn. And you can't learn by just physically doing it. And so we have to create a virtual reality simulator. And you guys know we're quite good at virtual reality simulation. And it has to be sufficiently real that Leonardo thinks that it's really learning. And it has to be physically accurate, meaning it has to obey the laws of physics. And so what you're looking at, what you're about to see here, is a virtual reality simulator of Leonardo learning how to be Leonardo. And it's photoreal, so Leonardo can't tell whether it's in the reality or not, and it obeys the laws of physics. What you're seeing also runs the entire computing stack. It is all completely based on hardware in the loop, so the entire computing stack is working right in front of you. Okay, so let's take a look at that, Rev. This is Leonardo in virtual reality. And Leonardo is learning. And these are all the different paths that it could have taken, and then showing the path that it did take. It's just quietly in its lab, learning how to be a good robot. We could put objects in its way. Look at that. We put objects in its way. It moves away from it. Can you see that? And once we stop getting in its way, it could get back to work. It is running hardware in the loop, which means the computer that is here running Leonardo and the computer that's running that virtual reality simulator, same computer, same AI, everything is working. The perception of the cameras, the perception that comes from the Z-depth camera, the laws of physics, the weight of the cubes, all exactly the same. Simulate everything. And this is how we're going to create robots in the future. And part of the Isaac SDK comes with the simulator. Without simulation, it is impossible to create robots in the future. They need this virtual reality environment to learn 6 degrees of pose, perception for visual, perception for touch. Now, of course, we would like Leonardo to learn a lot faster, right? And so,
Definitely.
Yeah. See, one of the great things about Leonardo is it's got a whole lot of friends. And it replicated itself. And so every single one of them are running on a real Leonardo computer, running the entire, the Isaac stack connected to this simulator. And it's learning. And every so often we'll checkpoint, select the smartest Leonardo, replicate all their AIs, and then start again. Ladies and gentlemen, Leonardo. Nathan, congratulations.
Thank you.
Nathan Radcliffe. Amazing AI researcher. This is a great achievement. It's a great milestone for robotics. So this is our stack. This is the Isaac SDK, the processor, Xavier, the Xavier robotics processor. I happen to have one in my hand, in my pocket. Here we go. Little tiny computer. Okay. The Xavier robotics processor, the Isaac software stack, the reference applications, Leonardo and Carter. Carter for navigation, Leonardo for manipulation. The simulation environments, one to simulate navigation, we call Isaac Sim. The other, we call Isaac Gym, so that the robot can learn how to be a good robot. All of this connected, hardware in the loop, so you're looking at running real software. Today, we also like to announce that universities across China are going to adopt Isaac so that we could teach robotics in schools and so that researchers could advance this field and help us discover the future of artificial intelligence, the next great adventure. It has been an amazing year. It has been an amazing year. Accelerated computing, the path forward has made some really fantastic achievements because of our collaboration. We discovered 3 new applications. One application is ray tracing. Another application is 5G. Another application, genomics analysis. We put RTX, we invented RTX, redefined the future of computer graphics, and we partnered with Tencent to put it in the cloud so that 800 million gamers who don't have access to sufficiently powerful computers can now enjoy PC gaming at the level that we should. We invented a new way of sharing and collaborating very complicated workflow. We call it Omniverse. Portals from applications be connected into Omniverse so that designers from around the world across different workflows could collaborate together. We created an application for AEC. Omniverse AEC is now available for early access. We brought CUDA to ARM. All of the body of work and all of the applications we accelerate, including one of the most important today, TensorFlow, now available on ARM. We made enormous progress in the last year in inference. We are accelerating the single most important model in the world on the internet called the recommendation system. As the world moves towards deep recommenders, we have the ability to power the internet. And of course, TensorRT 7.0 makes it possible for us now to compile all kinds of neural networks, from CNNs to transformers, and very importantly, RNNs, which makes it possible for the very first time for us to have interactive, real-time conversational AI from end to end. We announced our Orin processor, the next generation robotics processor, 7 times more powerful and includes all kinds of new technology for functional safety and security. And then lastly, we announced a brand new SDK we call Isaac to enable the next generation of AI we call robotics, and demonstrated to you, Carter and Leonardo. I want to thank all of you for your collaboration to make accelerated computing amazing, and thank you for coming and enjoy a GTC.